scuba tank, air charge, and performance calculations. So we're going to use a full-size scuba tank. So we have our mouthpiece, the air tank, and of course S.C.U.B.A is an acronym which stands for self-contained underwater breathing apparatus. So we have our primary and secondary regulators, and assume the S.C.U.B.A application is going to submerge to an underwater depth of 50 meters. So first we have to take consideration to the underwater pressure at 50 meters of water depth. So that is H meters depth times rho water density times gravitational acceleration, and that will calculate the pascals gauge pressure exerted on the tank and the scuba diver. So assume prior to submerging into the water, one is at an elevation above mean sea level of 45 feet MSL above mean sea level. So we can first start by calculating the atmospheres, 0.998, then multiplied times the standard atmospheric pressure at sea level, 14.7. So at 45 feet above mean sea level, the atmospheric pressure is 14.67 psi. So then we can convert the 490.5 kilopascals of water gauge pressure to its psi gauge pressure equivalent, and then simply add the atmospheric pressure to that value. So we calculate 88.6 psi absolute water pressure at 50 meters depth, and so that is also equal to 610.94 kilopascals, or 6.1 bar absolute pressure, 50 meter depth water pressure. So assume using a full-size scuba tank, we have a diameter of 7.4 inches of diameter and then a length of 26.1 inches. So the standard cubic feet air charge for a large scuba tank is 105 cubic feet of compressed air charge. So we have to then access the ideal gas law, since air is an ideal gas. So PV is equal to nRT. So assume that the outside air temperature prior to compressing the air in the tank is 65 degrees Fahrenheit. So we will maintain a constant air temperature while in the tank, because we're not dealing with any polytropic energy curves here. We're just dealing with a constant temperature and an increase in pressure. So then we can estimate there are 12 deep breaths per minute to sustain safe and functional underwater application, and a deep inhale breath for human lung capacity is 6 dry liters of air. Next, we take the 105 cubic feet of air and find out what the air density is at 65 degrees Fahrenheit, outside air temperature at an atmospheric pressure of 14.67 psi. So we can simply multiply the atmospheric pressure times the molar mass of air, 29 grams per mole, and then divide that product into the ideal gas law constant for air, which is 10.73 times the Rankine absolute air temperature. So in this case 65 plus 460, 525 degrees Rankine. And so when we divide these two out, we get an air density of 0.755 pounds per cubic foot air density. So if we multiply 105 cubic feet times the air density, we calculate a mass air weight of 7.9 pounds mass air compressed into the tank. And so we know the molar mass of air is 29 grams per mole. We know there's 454 grams to a pound. So that is 3599 grams of air, then divided into the molar mass of air. So that then the end value is 124.1 moles of air compressed into the tank. Then the universal gas constant for any ideal gas is 8.314 joules per mole degree Kelvin. And then we convert the Fahrenheit air temperature value to Celsius. And then we simply add it to 273 to calculate the degrees Kelvin absolute temperature. So 291 degrees Kelvin, or 291.33 degrees Kelvin. So then we have to calculate the fixed tank volume, the structural volume. So we can use pi r squared, the diameter in feet, then divided into 2 for radius. That radius then squared. And then times pi. So we have a cross-sectional area of the tank of 0.29 square feet, for which we can just multiply times the length of tank in feet. So we divide the 26.1 inches into 12, 2.175 feet length tank. So when we multiply these out, we get the cubic feet structural volume of the tank, 0.63 cubic feet. So if we find its cube root, we can get the linear feet, then divide it into 3.28 feet to a meter, to then get linear meters. Then we cube that value. So this is 0.017 cubic meters of structural volume of the tank. So that will be our V component. And then we simply convert the volume of compressed air just as a side reference value if we need to use that later. So essentially we're compressing nearly 3 cubic meters of air into a 0.017 cubic meter tank. So obviously we'll have some pretty high pressure in this tank, high air pressure, and so we'll keep that as a side note. So our volume, structural volume is 0.017 cubic meters. So when we multiply nRT and then divide that value into the V component, we calculate a gauge pressure of 17.68 megapascals gauge pressure, and then we can just add the atmospheric pressure in pascals to that value to calculate the absolute pressure of the compressed air charge. So 17.78 megapascals absolute pressure, for which then converts to 2579 psi absolute, or we can also convert that to bars as well. 100,000 pascals to a bar, so it's 177.8 bar absolute. So that is our tank air pressure at 105 cubic feet compressed into approximately 0.6 cubic feet, which is 0.017 cubic meters. So at 12 deep breaths per minute at 6 dry liters volume per full human lung capacity. That translates to 72 liters per minute of air supply depletion, or 72 liters per minute depletion rate. Next, we focus on the liters relationship to cubic feet. So 1 US gallon liquid is 3.78 liters, or 3780 cc's, or 3780 milliliters. 1 US dry gallon or gaseous gallon is 4.41 liters of volume, or 4410 cc's, or 4410 milliliters. And so based on this, we can take 1 US liquid gallon is also equal to 0.134 cubic feet. And then we can get a differential across both dry and wet gallon liter volume and multiply it times 0.134. And this will calculate the cubic feet volume of a dry gaseous gallon. So 0.156 is the correct value. So based on that information, we can take 105 cubic feet of air and divide it into the cubic feet volume of 1 dry US gallon or a gaseous gallon. So this is 673 dry gallons of air compressed into the tank times 4.41 liters per dry gallon. So that's 2,968 liters of air compressed into the tank. And then we'll use a 0.8 safety coefficient because we don't want to deplete all the air. We need some backing pressure for safety. We're assuming there's no boost pump or air pump on the device. So we'll assign the safe volume of compressed air at 2374.4 liters available air supply. Okay, so now we can take that value and divide it into 72 liters per minute, and this gives us 33 minutes of underwater air supply time. Next, we have to take the buoyancy force consideration because we want practical control authority through the water as a function of submerging and diving or depth. So we have to take the 7.3 pounds of mass air compressed in the tank, and that is the weight of the air at 14.67 psi atmospheric pressure at an air temperature of 65 degrees Fahrenheit. Then we'll take the average diver weight of 165 pounds. However, the density of the human body is slightly heavier than water. It's about 1050 kilograms per cubic meter versus 1000 kilograms per cubic meter, but that depends on breathing rates, flotation methods. So the actual weight of a human being exhaling and inhaling is approximately, with respect to dynamic momentum, being able to accelerate through the water up and down, it's actually going to be about a 10% or 90% weight reduction. So we can take the negative rho times g times v as the buoyancy. So we just calculated a 37.5 pound sink force taken from its Newton value converted, and then we'll assign 10% of the weight, so 16.5 pounds force of sink force plus the weight of the air in the tank. So this approximately comes to 62 pounds of sink force or less. However, that is going to oscillate from as low as close to 0 to as high as above 62, but the average buoyancy force is with respect to control authority through the water. So there's about a 10% gradient on that. So it's about 50 pounds of ballast sink force for controllability to sink at a practical rate. So we don't want to have so much buoyancy force positive that we can't even submerge into the water, and that's not an issue based on the human body's density to water. It's about a negative 0.1 respect, a little bit heavier, but when you start swimming and treading water, you then have this wide range that's very controllable. So it could be as low as close to 0 or 20 to as high as 60, which is very good for being able to submerge fast enough and sink with enough dynamic momentum, mass times velocity, diving. So 50 is about the buoyancy force with respect to sink force is about 50 pounds plus or minus 25%. So we have a pretty good sink ballast metric here, and average tank weight is about 27 pounds empty without air charge. So at 50 meters water depth, the tank also must withstand 100 psi absolute water pressure. So that tank could most likely be constructed from chrome moly steel material. So we can put all this information together and have a relatively accurate data set for a large size scuba tank device, including the average weight of divers. Okay, so then we have one last metric to make, and that is what do we set the secondary regulator at for PSI, discharge air pressure. So again, we can visit our ideal gas law equation, and this time we can divide the 72 liters per minute into 60. So we need 1.2 liters per second of air, and so we can divide that into 4.41 liters per dry gallon. So we got 0.27 dry gallons per second of airflow times our cubic feet per dry gallon. And then we have our cubic feet per second airflow. We convert that to cubic meters. So we need 0.012 cubic meters per second of air discharge to the diver from the tank. And so if we take the cubic feet of charge with respect to the weight of that charge per second, it's going back to the 0.042 cubic feet per second times the air density we previously calculated. We would then have to discharge 0.0032 pounds per second mass air, and then times 454 grams to a pound. That's 14.53 grams per second of air. And so if we divide that into 29 grams per mole for the molar mass of air, we have to discharge 0.5 moles of air per second. So this then becomes a negative value, negative n, or negative 0.5 times the gas law constant times the absolute temperature in degrees Kelvin divided into the structural volume in cubic meters. So we have a decrease in pressure, a gauge pressure actually, of negative 71.2 kilopascals, for which we convert then into PSI as an absolute value. So the approximate PSI at the regulator is about 10 PSI G, or 10 1/3 PSI gauge pressure. So usually there's a liters per minute reading on the gauge too, and it's also adjusted to the user or the diver's preference, but this is a ballpark calculation. So it's approximately 10 PSIG is a regularity setting. So that then completes the scuba tank performance calculations with respect to the air charge. So that's been renamed to scuba tank performance calculations. Thank you for watching this video and have a great day.